Okay, so we're going to talk about two types of functions today, circular functions and periodic functions. So before we really introduce exactly what a circular function is, we need to define the unit circle. And it's something I've alluded to a little bit before. It's going to be super important when we're talking about both cosine and sine. So the unit circle, it is a circle with a radius of 1. A circle with a radius of 1 unit centered at the origin. Okay, so it's like the easiest possible circle that there is. Okay, so let's backtrack to what we did in chapter 9 with the conic sections. If you were to write the equation for that circle, it would look like this: x squared plus y squared equals 1. It's like, just so we know, that's the equation of this circle right there. Okay, the center is at the origin, so it's not like an x minus 2 squared or anything like that. It's just x squared. Same thing with the y, it's just y squared. And if the radius is 1, we plug in a 1 for r squared. That would be 1 squared, which is still just 1. So this right here is the equation for this circle that we've got drawn over here. It's centered right at the origin, and then the radius is 1. Okay, so this part is very important. Hopefully you remember from 12.3 when we defined sine, cosine, and tangent. Well, for cosine, we defined it as x over r. For sine, we defined it as y over r. So let me write those things down really quick. So sine, remember the definition that we used in section 12.3 was y over r. Well, here's what's so special about the unit circle. In the unit circle, the radius is 1. So it's really just y divided by 1. We know, of course, that anything divided by 1 is just itself. So sine of theta is just equal to the y value if I'm sitting on the unit circle, because the radius is 1. So whatever this y value is right here, that's the value of sine. And then cosine, very similarly, cosine is defined as x over r. But again, the reason the unit circle is so special is because the radius is just 1, and x over 1, of course, is just x. So we love the unit circle because inside the unit circle, all of the x values are just the cosine values, and all of the y values are just the sine values. So it's a wonderful thing. So anytime you see a coordinate point, and it's just some random xy coordinate point, like we have labeled right here, for example, that point we may as well also call it cosine, comma sine, because x is the same as cosine according to this, and y is the same as sine according to this. Okay, so the circular functions that we define, sine and cosine, are defined by looking at a circle, and so we call those circular functions. All right, let's look at our first example here. It should be pretty straightforward. Terminal side of angle theta in standard position intersects the unit circle at the point negative 4/5. That would be somewhere like 3/5, and then negative 4/5 would be maybe like here. That might be the point they're talking about. So I'm just going to draw that on here rather than draw my own new unit circle. That might be the point that we're talking about right there, for example. So what I just wrote right here is exactly what we're going to be using in example 1. The point 3/5, negative 4/5, this is the x coordinate, this is the y coordinate, just like we have right here. We know it's equal to cosine of the angle, comma sine of the angle. So normally if we were trying to find cosine, we'd define x over r, which would be 3/5 over 1, because my radius is 1, as long as I am in the unit circle. Okay, so cosine of theta must just be equal to 3/5, which is the x value right here, and sine of our angle theta must just be equal to the y value, which is negative 4/5. Again, they're both technically divided by 1, because r is 1, and according to these formulas, you have to divide by r. So these are your values. Very straightforward. If they just give you a point on the unit circle, cosine of theta is the x value, sine of theta is the y value. Okay, so those are circular functions. We're going to come back and do a lot more work with the circular function after we look at periodic functions really quickly, because it's kind of a combination. As soon as we move into 12.7 and 12.8, we're going to be drawing sine graphs and cosine graphs, which are not only circular functions, they're also periodic functions. So let's quickly jot down, not really a definition, just some facts, I guess, about periodic functions. A periodic function, it has y values that repeat. On regular intervals. That is what is so special about periodic functions. Okay, so a function that is periodic, it's repetitive. It has a cycle and it goes through that cycle an infinite number of times. So there are a couple of examples on this sheet right in front of you. So we labeled a couple of things on here. One cycle, it starts here and it goes through a pattern of y values until it lands right back where it started. And then it goes through that pattern of y values again until it lands right back where it started. You can keep going off to the right, repeating this zigzag. You can keep going off to the left, repeating the zigzag. But it's repeating these same y values on a cycle, just over and over and over again. So when I use the word cycle, a cycle is one complete pattern. So that pattern of y values that we're talking about, once I go through the whole pattern, we call that a cycle. And then the period of a function is basically how long it takes to go through that whole cycle. All right, so period is defined as the horizontal length of one cycle. So according to this and according to this, it takes 360 degrees to go through one full cycle, and then every 360 degrees, it repeats itself. So let's look at an example. Here's the periodic function right here. All we have to do is determine the period of the function, which means the horizontal length or how long it takes to go through one cycle. Okay, so we're going to say our cycle starts right here, and it goes down, and it goes over, and it goes back up, and then it's at this point that it starts to repeat itself again. All right, and then it goes down, and it goes straight over, and then it goes up, and then that's the end of another cycle. So from here to here, that's the length of a cycle. From here to here, that's the length of another cycle. So technically what you're doing is you're taking the end of a cycle and then subtracting the beginning of a cycle. And so what we came up with here was pi. We could also use this cycle from here to here. The end of the cycle is 2 pi minus the beginning of the cycle. It started at pi. So again, that is a length of pi. So the period of this particular function is equal to pi. That's what we were trying to find out with this question. Okay, so just a little fun fact here, because now we're going to start talking about wheels in the next question. The rotations of wheels, pedals, carousels, any object really that rotates around in any sort of circular formation, we consider those to be periodic functions because the things repeat over and over again. So the next question we're going to be looking at has to do with a wheel, a bicycle wheel that's rotating around. So go ahead and flip to that next question. Okay, so if we read through, it says the pedals on a bicycle. So these are pedals. They're all in different positions here. They rotate as the bicycle is being ridden. The height of a pedal is a function of time. Like as time passes, the height of the pedal changes. As shown in the figure on the right, below. The figure shows a cyclist that completes one rotation every 2 seconds. All right, so the pedal starts here at 0 seconds. At half a second, it's made a quarter of the way around. At 1 second, it's down here. 1.5 seconds, and then it finishes its cycle at 2 seconds, okay? Another cyclist, a different cyclist, pedals the same bike at a rate of 1 revolution per second. So basically what we're gonna do, we've got this picture in front of us that describes one cyclist, the first cyclist. We're gonna pedal that same bike, but faster, twice as fast, at a rate of 1 revolution per second. So here we're at 0 seconds. It's going to go all the way around its cycle and land back here in only 1 second. Okay, which means it'd be at its halfway point down here at 0.5 seconds. Here's your quarter mark. That would be 0.25 seconds. And then here's your 3/4 mark. That would be 0.75 seconds. So since it takes half as long, all of these values are half. 0.25 is half of 0.5. 0.5 is half of 1. And let's throw in seconds, seconds. All right, so those are the new values that we're going to be using to answer part A and part B. So part A, we want to make a table for this bike with these values on it. All right, so time is our first variable. We're going to use all these, 0, 0.5, 1, okay, and then height. Height is a function of time. The height of the pedal changes as time changes. So at time 0, we're all the way up at the tip top here. That is 18 inches. And then every single second, like a full second later, it's right back up there. Right back up there at 18 inches. And then it goes another second. So at 2 seconds, it's right back up there. Then it goes around in another second. So at 3 seconds, it's right back up here. Okay, so now let's look at 0.5. Half a second, we're down here at the bottom. The bottom is 4 inches off the ground. And then here's 1. Half a second later, it's right back here at 4. Here's 2. Half a second later, it's right back down here at 4. And then at 3, we end up at 18. It would repeat over and over and over and over again. So let's identify the period and graph the function. So the period is how long it takes to go through one full cycle. And it basically told us right here, it takes 1 second to go through one full cycle. So we don't have to do a ton of work on our own there. Let's graph this function. Okay, so the height and the time. Okay, so we've got 1 second, 2 seconds, and 3 seconds. Okay, then we can split it up into half seconds here. Okay, and then here, let's go 4, that would be 8, 12, 16, and then 18 would be just a little bit higher. So at 0, we're here at 18. And at all the 1 second marks, 1 second, 2 seconds, and 3 seconds. We're all back up at 18. And then the half second marks, we're down here at 4. 1.5, 2.5, we're down there at 4. Now the one thing that we probably should throw in there is that on the quarter seconds, 0.25 and 0.75, there's a height of 11, this height right here. Okay, so 11 would be maybe like right there. So it's not a bad idea to throw some of those points in. So at the quarter mark and the 3/4 mark, quarter mark, and the 3/4 mark. Okay, so that'll give us a really good idea. Now, it's not a V shape. It is not the same shape that we had on the previous page because it's going in a rolling sort of curvy motion. All right, so it rolls here, goes through that point, rolls around, and so it's just a very like up and down, curvy sort of graph, like that. Okay, so that is what happens with the wheels and the pedals as you are circling around and pedaling at a rate of 1 revolution per second. Okay? The last thing we're going to look at is the complete unit circle. You may have seen on the next page we have an even scarier version of that circle that you didn't like from the previous sections. So this part is very, very, very important. If we are looking for the exact values of cosine and sine for any of our special angles, meaning 30, 45, 60, and any other angles that reference back to 30, 45, and 60, we can use that doing a unit circle. So here's the very, very, very important part. The cosine values are just the x-coordinates, and the sine values are just the y-coordinates. So that is super, super, super important. And then what happens, they repeat every 360 degrees. We've been talking about that. You can keep going around the circle over and over and over again, and you would just repeat those values. Because like 360, for instance, lands at the same place that 0 did, which means 370 lands in the same place that 10 did, and you can go backwards. Negative 10 would land in the same space 350 does. So we already talked about that with coterminal angles. So we know that function's periodic. It just repeats over and over and over again. Okay? So let's look at this unit circle, this scary looking thing that we've got here. So I'm going to go through, I'm going to quickly fill in the degrees because this should be familiar. We start at 0 degrees, and now let's first go up by 45. Here's 45, plus 45 would be 90, plus 45 again is 135, and this is 180. So all I'm doing is I'm adding 45 each time. Plus 45 gives me 225, then 270. Plus 45 give me 315, and then I land at 360. Remember, like I said, it is periodic. You could go around over and over and over again. But for the unit circle, we only write down the values that I get for going around once. Okay, and then this next degree measurement is 30 degrees. Now I'm going to go up adding 30. So 30 plus 30 is 60. Plus 30 again is 90. Already got that one. Plus 30 is 120. Then 150. We've already got 180. Plus 30 gives us 210. Again gives us 240. We've got this 270 already. Plus 30 is 300. And one more time, we get 330 right here. Well, I guess one more time really would land you at 360, which we already had. So those are the degrees. Degrees should be familiar. I'm hoping that I don't really have to spend much time explaining where the degree values come from. Okay, so next, we also start at 0 radians. And if we go all the way around and land back here, we know this is 2 pi radians. Okay, halfway around would be half of that, which would be pi. Halfway in between 0 and pi, let's do 0 and 1. Halfway between 0 and 1 is 1/2. So throw a pi in there. This is like 1/2 pi, pi over 2. If this is 0, 1/2, 1, this would be 1.5. And 1.5 is the same as 3/2. And just throw in a pi. Okay, so one of the values that you should know, this value right here is pi over 6. You could go through the motions, you could convert 30 degrees into radians. I promise you, you would get pi over 6. So it's like 1/6. I'm going to add 1/6 to itself over and over and over again. If I add again 1/6 plus 1/6 would be 2/6. So this should be 2 over 6 right here, which reduces down to 1 over 3. And then toss a pi in there. So this was 2 over 6. This would be 3 over 6, which we know reduces down to 1/2. This would be 4 over 6, which reduces down to 2 over 3. Throw in a pi. This would be 5 over 6, which doesn't reduce, but still throw in a pi. 6 over 6 would just be 1, so throw in a pi. 7 over 6. 8 over 6 reduces down to 4/3. As always, throw in a pi. Here's 9 over 6. It reduced down to 3/2. 10 over 6 reduced down to 5 over 3. And lastly, 11 over 6. Don't forget to keep throwing the pi in with all of these. Now finally, our 45 degree family. So this, again, you could convert it by hand if you want to. I promise you're going to come up with pi over 4. So now we're going to go around and just add pi over 4 each time. So here's 1/4. Here's 2/4, which is 1/2. Here's 3/4. Throw in a pi. Here's 4/4, which just reduces down to 1. Here's 5/4. Here's 6/4, which reduces down. Here's 7/4. And this is 8/4, and 8/4 reduces down to 2. So that's what we've got so far. That's the stuff that we already had. Okay, so now this, if we were to turn these into some triangles right here, and we were to make a nice little triangle out of this, if you were to go back to your special triangles, you would find out that since the radius is 1, because this is a unit circle, so if my radius is 1, in a 30, 60, 90, this is going to be half that. Okay, because this is always 2 times the short side. We learned that when we were doing 30, 60, 90s. So this value right here is 1/2. Well, that's also the y value. So that means the y value is 1/2. Okay, and then this length, this is the other leg. According to special triangles, 30, 60, 90, this leg is √3 times the short leg. So this becomes √3 over 2. And I am hoping that those values look familiar, because remember, cosine of 30 gives you this value, sine of 30 gives you this value. And you've had those on a table before. So now here's where we reference all the way around the unit circle. This coordinate point right here is very, very remarkably similar to this coordinate point right here. Notice they have the exact same y value. So they both have a y value of 1/2. And they've got the same but opposite x value. So whatever this value is, this is just the negative version. So this is negative √3 over 2. So remember, if I asked you to find the cosine of 150, you would find the cosine of 30 and then make it negative, because that was in the second quadrant. Now this coordinate point right here, they're both negative. The x value is the same but opposite. and the y value is the same but opposite. Like this y value is the opposite of this y value right here. And then finally over here, this coordinate point makes the same triangle. These would have the same x value. They're lined right up on top of each other. And these 2 points would have the same y value, which is the negative 1/2. Okay, so we've got 4 of our points right now. Let's look at even easier points. The values that lie right on one of the axes. So if we know this is a length of 1, and this is the origin right here, this point right here just went over 1 unit. This would just be the point 1, 0, which makes this, to the left, the point negative 1, 0. If all I do is go up 1 unit, that's the point 0, 1. If all I do is go down 1 unit, that's the point 0, negative 1. Okay, we're getting there. We got a couple more families to go through here. This family right here, 45 degrees. If you make this triangle right here, okay, so that's this triangle. This has a radius of 1. I'm not going to go through the details, but according to what we know about 45, 45, 90s, both of these side lengths would be root 2 over 2. Remember, that's one thing about 45, 45, 90s, that they're both the same. So now I can do the same thing. I can transfer this point all the way around the unit circle. Over here, my x value would be negative. My y value would be positive. Down here, both negative. Negative x value, negative y value. And finally, my fourth one right here, positive x value, negative y value. Okay, and last but not least, this triangle right here is also a 30, 60, 90, but it's kind of the opposite of this 30, 60, 90. Here, the short side was y, here the short side was x. So since this short side was 1/2, this short side was 1/2, but this time it's the x value. And since this long value is root 3 over 2, this long value is root 3 over 2, which makes it the y value. Now one last time, let's transfer all the way around. Here, just the x value is negative. Down here, they're both negative. And our last one right here, the x value is positive, but the y value is negative. Okay, so now we know all of those values. I promise eventually you will be able to fill that unit circle in. And notice some of the tricks that you had kind of memorized, I suppose, are now right on here. So that's what we can show you with something like this. Using the unit circle, cosine of 45, that was one of the things that was on your chart that you had. Maybe you have it memorized, maybe not, but you can get it right off of the unit circle. So you find the 45-degree angle, and cosine is just the x value. It's as simple as that. So it's root 2 over 2. And that was something that was on your chart before, but now, if you understand how to use the unit circle, it's pretty straightforward. Cosine of 150. Find the 150-degree angle. Cosine is the x value. Easy as that. Negative root 3 over 2. If you had had this on the quiz you just took, you would have had to find the reference angle, which was 30, and you would have to know what the cosine of 30 is, and then you'd have to know that since you were in the second quadrant, cosine was negative, a lot that goes into that. When if you know the unit circle, it's very easy to pick out. And last one of these, sine of 270. So you find 270, sine is the y value, so sine of 270 would be negative 1. Okay, so really quickly, let's look back at these. We are going to start graphing these starting tomorrow. This is what the sine and cosine values would look like. If I use the angles right here as my x-axis essentially, if I graphed all of these x values, 1, root 3 over 2, then root 2 over 2, then 1/2, then 0, then negative 1/2, you can see that's exactly what this cosine graph is doing right here. I'm using the angle essentially as my x and the value of cosine as my y, and then same thing with sine. If my angle is 0, the sine is 0, starts right here. If my angle is 30, the sine is 1/2, right here. If the angle is 45, my sine is root 2 over 2, and you're just following. And it would just repeat over and over and over again because this is a periodic function. Okay, last quick little examples here. We want to find these values too. Cosine of negative 3 pi over 4. Okay, here's 3 pi over 4, right here. So from 0, I can go forward to 3 pi over 4, or I can go backward to the exact same spot, which would be this far. So that's this value right here. Okay, and the cosine is the x value, so that would be negative root 2 over 2. Okay, and then the sine of 420. Okay, so stay start at 0, go counterclockwise all the way around to 360. 420 minus 360 leaves 60 degrees, so I go 60 degrees more, and I land right here. And I'm looking for the sine. Sine is the y value, so the y value would be root 3 over 2. Okay. By the way, this is what we mean when we say exact value, not a decimal value. A decimal value is an approximation. These are exact values when square roots and fractions and things like that are involved. Okay, so coming up next will be the actual graphs of these sine and cosine functions that we very, very briefly introduced right here.